Hello, it's time to learn about complementary angles. The next topic we're going to look at are complementary angles. These are given in the textbook on page 264 with some fairly complex diagrams that I'm going to attempt to break down for you, but in the end I'm going to show you something that hopefully means you won't need this method anyway. Let's have a look at the first quadrant of our unit circle. So just worrying about this bit here, and we know that our standard little diagram looks like this, where sine x is our height and cos x is our distance away from the y-axis. Now, so far, we've also been able to use symmetry to predict anything over here as well, or down there, or down there. We can use symmetry to do those. But what we're also going to use are complementary angles to predict something that might be going off the y-axis. So for example, if we draw another angle that goes up there, and this angle here is theta, can we calculate this length here or this length here using the information that we had before? And it should be obvious through symmetry. If I draw a dotted line that goes up like that, it should be obvious through symmetry that this line here, sine x, is going to be exactly the same as that length there. So this length here is sine x, but can we also find another definition for it? Well, we know that this angle here is pi, and this whole angle is a right angle, which is pi on 2. So it should be obvious that if we've got, if we've got that angle there, which is pi on 2, and now I'm going to talk about this one. So let me undo a couple of things. Hang on, I'll just get rid of. Okay, so this angle here is theta. How big is this angle here? So I'm talking about if we're measuring our angle properly, starting from the x-axis as 0, and we're measuring up like that, how big is that angle? Well, it should be obvious that we've got a right angle there, and so that angle is actually pi on 2 minus whatever our theta angle is. And so pi on 2 minus theta is the size of that angle, and this length here is the distance off the line, because really it's the same as, oops, let me undo that because I'll use a different color to try and highlight what I'm doing now. And so that length there, sine x, is the same as our horizontal line. If I drew this from this point here, if I drew that downwards instead, I'd get to that. And so this green line now is the same length as that sine x, but it should also be obvious that that's the cos of this angle, as in the x value, the distance off the line, of the y-axis, of this point here. And thus, cos of that length there is equal to, as we've shown, sine of that base angle, so sine of theta. That's what the textbook diagram is trying to get to. We've got a similar relationship for anything that's going off to the left-hand side or going off the y-axis in the second quadrant, and we can have a similar rule for the third quadrant and the fourth quadrant. And essentially what this allows us to do is to swap between cos and sine. Here, one of them is cos and one of them is sine. Those could be vice versa as well. We could quite easily come up with similar logic, I'm not going to go through it now, that tells us that sine of pi on 2 minus theta is equal to cos of theta. And so we've got a way of swapping between cos and sine, but to do so involves going off pi on 2, which is a little bit different to what we'd normally do. What I mean by that is, when we're normally tackling these problems, if we come up with a base angle, let's have a talk about that. If we know that our base angle here is theta, and we know then this length here is sine theta, we know through symmetry that this point here must have the same sine value, and this point here must have a negative version of the same sine value, and this point here must have a negative version of the same sine value. So through symmetry, we know that all these points have the same sine value. And thus, if we're going around our circle, we know that theta, or pi take theta, or pi plus theta, or 2 pi minus theta, or 2 pi plus theta, going on forever, as we keep going around this circle multiple times, all of those points are going to have the same value. But you'll notice that all of those points are measuring upwards vertically off the x-axis. What happens if we want to find out something like 3 pi on 2 plus theta? Well, we're not measuring up off the vertical axis anymore, because 3 pi on 2 plus theta, 3 pi on 2 is down here, and plus theta is going around that far. So we can't just jump to the same conclusions that this must be our base angle, because in fact it's not going to be. But let me try and draw this a little bit bigger and explain what's going on here. So I'll just draw that diagram but larger. 3 pi on 2 is obviously down there, and if we were asked for what is cos of 3 pi on 2 plus theta, we know that that angle there is theta. We know that that base angle up there is also theta. Let's have a look at what identity we're looking at. We're looking at cos, or sorry, I should have said what ratio we're looking at. We're looking at cos. Cos is the distance across from the y-axis. So we're looking for what's the length of that line there, and it should be obvious that that's the same as that length there through symmetry. And we know from our unit circle and our base diagram that that's the same as sine theta. So if you are ever asked a problem like what is cos of 3 pi on 2 plus theta, we can draw a little diagram that looks like this and turn that into stating that's the same as sine theta, and thus look up whatever theta angle is and find that from our table of exact values, or possibly from the question that's given. I'll give you an example question that will use these skills and we'll see how we go. A question might say something like sine x is equal to 0.59 and cos x is equal to 0.81. So given these bits of information, can you determine what is sine of pi plus x? Or can you determine what is cos of 2 pi minus x? Or can you determine what is sine of pi on 2 plus x? So for each of these, the first two here, you'll notice are pi or 2 pi. They're going off the x-axis. They're going off pi, which is over here, or 2 pi, which is over here. And so they're doing exactly the same thing that I talked about here. They are going off the x-axis in a vertical direction, going up there, or in the first case, let's look at where is sine pi plus x. Sine pi plus x is going to be going around to pi and then a little bit more, so we're going to be down there. And let's also think about what is 2 pi minus x. That's going around 2 pi minus a little bit, so we're going to be down there. In both of these cases, we are going off the x-axis, going in a vertical direction. So both of those, we don't need our complementary angles, any of this stuff that I've talked about today. That's relying on knowledge that we did yesterday, it's relying on knowledge we did last week through symmetry. We know that that first one, in green, sine of pi plus x is just going to be, well, it's sine, so it's negative, and that's going to be negative sine x. And we already have a value for sine x, which is 0.59. So in this case, that's just going to be negative 0.59. In terms of cos 2 pi minus x, we're going down there, but we're actually looking for the cos value, so we're looking for that value across there, and that's going to give me a value of cos is positive in this quadrant, so that's going to be the same as cos of x, and so that's going to be a value of 0.81 without any negatives attached to it, because we know cos is positive in that quadrant. So that skill, if we're going off the x-axis from pi or 2 pi or any of those values that are an integer value of pi, there's no tricks. That's just how we tackled those problems last week. But if we've got something that's asking us to go off pi on 2, that's where we need to think, okay, well, pi on 2 has me up there, and I'm now, I'll do this one in red from now on. We're going up there, and we're going pi on 2 plus x, so that's putting me in this position here where that value there is x. and I know that sine must be positive in this quadrant, so my answer is going to be positive. And my base angle is x over here, but I'm looking for sine, which is the height, and it should be obvious that that length there is the same as that length there. So we're going to be swapping sine to cos, and thus get a positive value. So even though this question is asking us for a sine value, we're going to use this value here, which is our cos answer of 0.81, and double check that it's positive because we're in the quadrant where sine is positive. So that's tackling those sorts of questions. I should also point out that there's another way of thinking about these, or at least a simpler diagram that can be done to represent this, and that is from any triangle, any right-angled triangle. If we know that that value is x, and this is a right angle, and a right angle is 90 degrees, which is pi on 2, then how big is that angle there? That angle there is going to be pi on 2 minus x. And that tells us that if I just label these as sides A, B, and C, that's going to tell me that sine of x is equal to opposite over hypotenuse, so that's going to be B over C, and cos of this angle here, pi on 2 minus x, is adjacent over hypotenuse, so that's B over C. So these two things are the same. So we can come up with this identity, this relationship that sine x is equal to cos pi on 2 minus x through a simpler right-angle triangle than we had up here. So a simpler diagram than this one, all it really requires is a right-angle triangle. That allows us to get the identity. From getting that identity, we still tackle questions in exactly the same way. So if I was tackling this question here and trying to think about a right-angle diagram, let me write down those numbers again. We've got sine of x is equal to 0.59 and cos of x is equal to 0.81. We can't really do much in terms of our diagram apart from drawing a right-angle triangle, labeling this one here as x, and knowing that if this is A and this is B and this is C, then A over C is equal to 0.59. And from there, if we remember that, we still don't know how big side A is, or we don't know how big side C is. We could take some shortcuts by saying, let's assume we're in the unit circle, which would mean C is equal to 1, and then A is 0.59. So there are ways of doing that, but I'm not going to overcomplicate it. My point is that just from here, we can easily come up with ratios for what is pi on 2 minus x. This isn't necessarily going to work though if you're asked for more complex things like pi on 2 plus x or 3 pi on 2 minus x, 3 pi on 2 minus x. So if you get something that looks like either of these, having a good thorough understanding of this sort of diagram here is going to help you. There's a lot to unpack there. Most people in this course tend to find this complementary angles identity one of the hardest things in trigonometry. So please ask lots of questions and do tackle some exercises and see how you go. Let me know if you've got any problems. Thank you.